Good morning. We are Max, Mingzi, Joshua, David, and Nick, and we are Team 2588139. Owning a box of Hagoromo chalk is every young mathematician's dream because of their silky touch and their delicate sound. But unfortunately, our school only has the regular kind of chalk, and you can imagine it makes a lot less pleasant sounds. After brainstorming some possible factors of why this might be, we decided on investigating how varying a chalk's drawing angle might affect the annoyance of the sound produced. This particular field is known as psychoacoustics, and it is where our definition of quote-unquote annoyance comes from. We used Eberhard Zwicker's research on annoyance to see some properties of sound that contribute to this notion, as we can see on the screen. This flowchart here summarizes our approach from how to get from angle to annoyance. Now, we did not find a purely theoretical way to get from here to here, so instead we first conjectured that the surface area of the chalk is a significant factor, and I'll call this quantity just surface area. We modeled this chalk as a cylinder that crumbles uniformly, and we use this crumble as a downward translation of the cylinder into a plane. We change our reference frame from here to here because it is much easier to mathematically model. Furthermore, we notice that all the possible intersections between the chalk and the blackboard are found by this ellipse, E. We split our analysis into case 1 and case 2, which are both dependent on the dimensions of the chalk. The first case is when 2r10 alpha is greater than or equal to h, which is where r and h are the radius and height of the cylinder, respectively. From doing the following trigonometry on the ellipse E, we can see that it has an equation shown here. The surface area of intersection can be found by performing an integration over certain bounds. So in this case, subcase 2.2, we can see that the locus of intersection is this portion of the ellipse, where these two bounds can be found by doing some trigonometry. The same logic is employed for the rest of the subcases. The second case is when 2r10 alpha is less than h, which is when the chalk is relatively longer than the tilt. Case 2 is different from case 1 because of this particular subcase, 2.2, when the contact area is a full ellipse at one period. But the other two subcases use the exact same integrating over the bounds methodology. Now, to get from surface area to annoyance, we had to do an experiment. Our methodology uses a custom 3D printed cart which held the chalk at a fixed angle, as we can see here. Since we found precisely fixing the chalk at an angle with a protractor was very, very challenging because of the small dimensions of the chalk, we instead varied the major radius of the contact area while keeping the minor radius constant to vary the surface area, since, as meant from the previous section, we found that each surface area corresponds to a particular angle alpha. Here's a diagram of our experimental setup. To pull the cart, we used this pulley system here, which provided a constant driving force. We then used Audacity's spectral editing software to dampen the sound produced by the cart's wheels. The audio was then processed through MATLAB to obtain the psychoacoustic metrics and annoyance so that we could get the raw data for our analysis. After gathering all of our data, we decided to use a polynomial regression of degree 2. Intuitively, we thought that as surface area increases, sound sharpness increases, and as surface area increases, loudness and roughness also increase. These factors both contribute to annoyance, so we expected a local minimum within the domain where both of these factors cancel each other out. These qualitative observations led us to conclude that a quadratic function, which was a good approximation since it goes down and then up. This function here is a result of our regression analysis. These values are specific. Are specific to the chalk that we used, but the analysis can be generalized by using a, b, and c as variables. Also notice that the function is not defined for s equals 0, since this corresponds to no chalk and hence no sound created. So in our paper, we established two different ways of measuring how annoying a sound is at any given orientation of a chalk. The first is instantaneous annoyance, which is how annoying the sound is produced at one particular instant or at one drawing distance, which is found using this function here. And the other is an accumulated annoyance, which is found by taking a sum or taking an integral over all the annoyances produced across a chalk's lifespan. Now let's move on to the analysis and first discuss minimizing instantaneous annoyance. From the graph of P, there's a turning point here, and getting to this surface area would correspond to the minimum possible annoyance point. This is the surface area function for a given chalk and angle for case 1, and varying our angle, this angle here, will vary the shape and the height of the curve, which corresponds to the aforementioned minimum surface area value, which is minus b over 2a. To minimize annoyance, we want this curve here to cross this line here at least once, which guarantees that on at least one point on the chalk's drawing path, the minimum possible annoyance point occurs. This actually means that there's a set of alphas that satisfy this minimization, which we will define the upper and lower bound to be alpha lower and alpha upper. So basically, we calculate whether the point occurs by setting this greater than or equal to this, and we do some calculation, and we find that the principal solution for alpha upper is this, where these are the defined constants here. The lower bound is purely due to the geometric constraint of case 1. It is worth noting that alpha upper does not actually exist for all values of R and H, shown as a graph where each ordered pair RH corresponds to certain dimensions of the chalk. Solving the aforementioned inequality, which was the curve being greater than or equal to the line, we can see that this shaded region here corresponds to all the pairs R and H such that the conditions for alpha upper exist. Now let's look at case 2. Notice the graph has a flat portion here. Physically, this corresponds to the contact area becoming a full ellipse for a pretty long period of time. When the flat section completely overlaps with the line, as we can see on the image on the right, we would say that this is the most minimally annoying point because the minimum annoyance point is reached for much, much longer than an instant, as opposed to case 1. To calculate this angle, we set the area of the ellipse equal to minus b over 2a to obtain the following angle here. Now, let's look at accumulated annoyance. We can actually find both the maxima and minima by taking the derivative of Tc2, which is the accumulated annoyance function, with respect to alpha and setting it equal to 0. This equation is actually very doable when R and H are given numerical values, but it is an incredibly, incredibly ugly function to calculate, and we decided it was unreasonable to find an analytical solution to this equation with general parameters. Moving on to maximizing, it can be easily seen that the maximum surface area of any given chalk is going to be this case. Using the Pythagoras theorem, we obtain this result. Hence, the domain of P of S we say is to be in between 0 and this quantity here, which we will be calling S max. Looking at the graph of P, the maximum value of P is dependent on the domain, restricted by S max, which would be this endpoint for both of these. On the screen are two cases. On the left, S max does not exceed minus b over a. On the right, it does. The vertical line corresponds to when the maximum annoyance, which I will call P max, exceeds the y-intercept of the graph, C. If the graph passes through the line, then we say P max equals C, like this point here. And if it doesn't, we say that P max equals PS max for this one. And for this one, we would say P max equals C, like that point. The conditions for P max equals C is on this inequality, which is dependent on the radius and the height of the chalk. And we can visualize this condition through this graph, where each point again corresponds to the chalk's dimensions. For any point below the curve, P max equals C, and for any point above the curve, P max equals S max. The angle alpha that corresponds to S max is this for when P max equals PS max, and we calculate this angle geometrically using this case. And for when P max equals C, we say that the alpha that corresponds to this can be found using the same methodology as case 1 minimization with the curve and the line and then putting it above the line. So we applied the formulas that we derived to calculate the optimal angle for our chalk, which is actually specifically this chalk here. And this is what we got. This is for instantaneous annoyance, and this is for accumulated annoyance. So if you want, you can ask us about the numbers later, and you can use these for your next lecture. In summary, we modeled the effect of angle and drawing distance on annoyance. This was done by first splitting the orientation of the chalk into two cases and relating the angle into surface area. We then experimentally found the relationship between surface area and annoyance through regression. And then finally we analytically derived the set of optimal angles to produce the maximally and minimally most annoying sounds. Thank you.